This video will cover some fundamental concepts in receptor binding. Back in 1902, a person named Emil Fischer won the Nobel Prize for basically putting in people's minds the concept that basically for two species, so this would be like a drug and a receptor, to interact in a specific way, they have to have a complementary shape. And the kind of corollary to that in everyday life is a lock and a key. Nowadays, a lot of times people criticize this concept as being too simplistic, but that's only too simplistic if you really look at it from the standpoint of the two species being rigid objects. Nowadays, nobody really considers that chemical compounds are rigid objects. We know bonds rotate and everything else, and proteins have a certain mobility to them. So clearly, it's two materials that have sufficiently complementary shapes, especially with regard to electronic charge, right? We talked about shape and charge. And the fact that when they come together, they might even both change their shape to improve that complementarity. Okay? That wasn't Emil Fischer's original idea, but there's no reason to think any less of this original thought. Now, again, this is a simplistic cartoon here. And the other thing is when we have a receptor, receptors are mobile proteins, and normally when we be talking about many of these types of things, we're talking about, say, a membrane protein. And within that membrane, they can change their shape. If they're in a particular shape, they will cause a signal to happen. If they're in a different shape, a signal may not happen. And this has to do with that shape of the receptor being able to create essentially a binding site for various proteins inside the cell that either basically transfer the signal, what we call second messengers, to other cascading reactions that ultimately lead to action within the cell. So you can have this idea that our receptor, right, doesn't necessarily have a single shape, and the receptor binding site might be considered as having different shapes. So now we're talking about this mobility, right, in complementarity of shapes. Now, we're showing basically two arrows going back and forth, and each particular receptor has a certain tendency to be mostly in one form or another to varying degrees. Okay? If we have a receptor that without any agonist present does not exhibit any signal, you would say that, oh, then it must reside mostly in the antagonist state, and it is only when agonist is present that the shape that's on the right for the active receptor conformation can be formed. So in other words, the complementarity is due to the binding of the agonist, which causes the change in receptor conformation. So that would be a case, what we would call, where we have no constitutive activity. And we're going to talk about this when we talk about pharmacology and activity. Now, so that would mean there's no signal taking place if there's no agonist present. Now, an antagonist, and we'll talk about this in terms of terminology, basically prevents the molecule, the receptor, from changing its signal as it has when it is unbound. Okay? I'm using a careful choice of words because there's a slight different term also called an inverse agonist. And we're not going to talk about that right here. We're just trying to introduce some topics, but we'll get to that in just a little bit later. Now, with the agonist and its binding, it now can signal, right? It can basically activate that receptor to cause this secondary signal to take place and an action to take place. And we can also have it such that different agonists have different degrees of being able to put the receptor into proper conformation. So we have this concept of what we call partial agonists. And again, we'll define all these terms again later in more detail. So you can have this situation where it's mostly in one form, or you can have this where even without any agonist or antagonist present, we have a certain population of the two different forms, which is the resting or inactive form and the active receptor form. And if we have, say, 10% in the agonist form and 90% in the antagonist form, then what would happen is we would have 10% of the maximal amount of signal constantly taking place even without any ligand present. And we call that a constitutively active receptor. So we're going to introduce that concept later when we talk about some aspects of agonists, antagonists, and inverse agonists. So binding itself, what is it? So we talked about molecular interactions in another video. And those molecular interactions lead to an overall affinity of one molecule for another. It is based on the complementarity of the shapes and charges that are present in the electrostatic surfaces of the two molecules. And this is what the two molecules see of one another. In other words, they don't see bonds per se. They don't see atoms per se. What they see is an electronic cloud of a particular shape that has charge distribution over it. Now, what is binding? We consider something binding when there is a preference for them to be together versus for them being separate, right? If they're separate, each one of them is doing what? Interacting with water. Well, there's a certain affinity of water for the substances that we have, particularly if they're polar. So that's something that's going to be competing with the two materials from interacting with each other, right? So we have a complex situation. We're not operating in a vacuum here. And this affinity is represented by an equilibrium constant. So we can mathematically represent what happens when we put some concentration, say, of a drug in the presence of a receptor, and that's going to result in a certain level of occupancy of that receptor. And that's going to be based on an equilibrium constant for that pair. So we're going to have an equilibrium constant for the two components, whether they are apart and together. Okay. So this is showing a ligand and a receptor bound on the left and equilibrium with the free ligand and the free receptor. The dissociation constant would be the product of the concentrations of the free ligand and the free receptor divided by the concentration at the receptor with the ligand bound. Now, this is going to be the inverse of the equilibrium constant for the association. In an association, right, we would have the free ligand and receptor on the left, right, and the double arrows, and then the bound ligand and receptor on the right. That's, you'd consider going from unbound to bound. The equation we have in the top looks like we're going from bound to unbound. So that's the relationship between KD and KA. So we can look at this also from the standpoint of the KD divided by the ligand, free ligand concentration gives us a ratio of the amount of free receptor divided by the amount of bound receptor. Okay? And it is that ratio of free and bound receptor that lets us know what is the receptor occupancy. Okay? It gives us an idea of it. It doesn't give you the number directly, that particular ratio. Okay? So, when the free receptor concentration equals the concentration of the bound receptor, then KD equals the concentration of the ligand. That's just the mathematics we have from the previous equation. So what we can conclude from this is when we have half of our receptor in the bound state versus in the unbound state, then we have a value, what we call the inhibitory concentration 50. So this is for a ligand that is an inhibitor. Okay? If it's an agonist, right, we would call it an EC50, which is effective concentration at 50%. Because what we are saying is that receptor occupancy is directly proportional to activity. Now, if we have this again here, note that the IC50 approximates the KD as long as the concentration of our ligand is much, much greater than the receptor, which is the usual case. Okay, there are going to be some differences in KD and IC50, particularly if the concentrations of receptor approach that or are close to that of the ligand. We're not going to worry about those situations. We're primarily talking about the normal types of situations where a ligand is, in fact, much, much greater than the concentration of the receptor. That makes things much more straightforward here. Okay. So now, how does this relate to binding? So we have this equilibrium constant or association constant, and we've talked about binding in terms of free energy of binding, and you have enthalpy and entropy. So how does all this work together? So our delta G equilibrium, right, equals 0 at equilibrium. And delta G at equilibrium, so 0 equals the delta G0, which is our delta G of binding, plus the gas constant, temperature in degrees Kelvin, and the natural log of the association constant. Okay, so if we take this equation and take it down and just basically say, well, what is our delta G of binding? Well, we would subtract the RT ln Ka, right, from both sides. And so that gives our delta G of binding is minus the gas constant times temperature in degree Kelvin times the natural log of our association constant. Now, if we want to convert this to natural log instead of from natural log to log base 10, there's a conversion factor of that, which is 2.3. And if we want to go from the association constant to the dissociation constant, which is the numbers that we usually use and report things in, so when we talk about potency and things like that, we will be talking about concentrations in terms of the dissociation constant. So here we have the relationship of Kd to Ka is inverse. So what that's going to do is if we have 1 over Kd, right, that is going to put a minus sign out front. So in the bottom right, we show this, that the log of Ka equals log base 10 of 1 over Kd, which equals minus the log of Kd. So where did this minus go? Well, notice in the red on the left when we talked about the Ka, it was minus RT. And notice in the blue, when we've converted it to Kd, it is now just RT times 2.3 times log base 10 of the Kd. So the minus sign basically negated the other minus sign. And so we end up with the equation in the blue equaling our delta G of binding. And that's the form of the equation we tend to use more often. Now, again, going back, we can say that, well, what is this also composed of? Our delta G is also essentially the delta H, which is the change in enthalpy. And this is going to be basically on looking at the change in enthalpy of all the different individual binding interactions that take place. Remember, we can have multiple in a given molecule. And then subtracting from that the temperature in degree Kelvin times the change in entropy. And there are several things that happen in terms of entropy. One, we have a mobile molecule in solution, right, and a receptor. And we now, when we're bound, we immobilize that, and so therefore that's a decrease in entropy. However, the drug molecule or ligand, right, is surrounded by water, and the receptor is surrounded by water, and for the two of them to interact, all of those waters, wherever this interface takes place between the ligand and the receptor, have to be lost, and then they go free in the solution. So we get a net increase in entropy, which is favorable. Okay, so here's the different components we have. In the case of enthalpy, we have favorable functional group interactions, right? All of the bonds that we talked about, hydrogen bonds, London interactions, ion dipole, and so on. The value of delta H is negative, so that's their enthalpy value. Unfavorable interactions would be if we have any kind of poor steric fit, right? Any kind of potential overlap, it's just not going to happen. And any other type of repulsion. So if we have two like charges next to one another, that would be a repulsive force. Okay. In the case of entropy, what's favorable is the loss to the bound water molecules, which we described. And here, delta S is a positive value. Unfavorable would be the loss of translation or rotational freedom, which is what we talked about, two independent molecules binding to one another, and we lose that freedom, degree of freedom. So you can see that what happens, what is our delta G if we have two favorable situations, right? We got good functional group interactions and we lose this bound water and we have favorable entropy. Well, our S is a positive value and delta H is a negative value, but remember it's delta H minus T delta S. So both sides of that equation would be negative, so both of them, right, are favorable, and they basically increase the absolute value of delta G, which would be a minus value, right? So if something is favorable, remember the delta G is going to be minus. Okay, so now let's talk about this in terms of receptor binding. The standard free energy of binding is the sum of the favorable enthalpic interactions, right? So basically we sum all those up, and the entropic interactions. So what does that look like? In the equation here in the middle, we have sum of the delta G's. So each of the binding interactions, right, is going to have a particular delta G associated with it. And we add all those up together, and that gives us our overall binding energy. And this is going to be equal to, right, the equation we just derived, which is the gas constant times temperature degree Kelvin, 2.3 times the log base 10 of our dissociation constant. And just as a note, the delta GI represents the number of individual binding interactions that we have, right? So the first binding interaction would contribute so many kilocalories per mole. That would be delta G1. The next one would be delta G2, right? And that contributes so many kilocalories per mole. And then eventually you just add all those up. And when you add all those up, that adds up to your delta G of overall binding. So the total binding is the sum of the individual binding interactions. That's what the two figures on the left with the equal sign between them basically say. And remember, favorable enthalpy, which is a minus value, and favorable entropy, which is a plus value, right, make delta G less than 0, because remember it's minus T delta S. Okay, so let's just quickly look at a couple of drugs interacting with the receptor and the types of molecular interactions that we have. So this is showing a small molecule thrombin inhibitor that binds at the active site of thrombin. So it occupies the site, but it is not a substrate, and so therefore it prevents thrombin from cleaving a protein which is in the blood called fibrinogen. Okay, so this is a mimic of a tiny part of fibrinogen in a sense, but it's something that is not a substrate. So it simply competes for the substrate and prevents it from being cleaved by the enzyme. So how the inhibitor binds, right? You want it to have an affinity that is good so that it can act as an inhibitor, right? So that it can compete effectively against the substrate. So what you can see is that we have the drug going from here down and in here. So we have a charge group in amidine that's going to be positively charged down in a pocket that has an aspartic acid, or aspartic acid 189 of thrombin here in it. And that's a ion-ion interaction in a pocket that is shaped to be able to accept a group such as this. Our active site serine 195 is here. And other aromatic groups that represent pockets for the binding of the substrate are around here. Okay, so these three-letter codes for the amino acids, and then the number relates to, these are side chains of thrombin and their location in the sequence of thrombin. The drug is in the middle here. Now, we have an ion-ion interaction here. We have hydrogen bonds here, depicted as we usually do with our oxygen, and this is actually to the hydrogen of that nitrogen here. And here as well, we're just not showing the hatched bond, right, between this and this, as well as this and this. And then we have the lipophilic groups, right? We have an alkyl chain, and the backbone of our proline residue is essentially an alkane-like, and those are interacting with various either aromatic residues, or other alkane side chains. And remember, we can call them individual names like induced dipole, or quadrupole induced dipole, but all of those are what we call van der Waals interactions because they don't involve ions and they're not hydrogen bonds, which we call separately. Okay, next we have a drug, rather complicated looking drug. It's kind of large. A lot of other drugs prior to many of the more recent types of drugs, many of the more recent drugs are actually larger like this, have an unusual situation in that this was one of the first compounds that was actually rationally designed by looking at crystal structure and optimizing interactions with the receptor. And they very specifically tried to optimize various types of hydrogen bond interactions. Now notice these are all different lengths. All these hatched bonds are different hydrogen bond interactions. And remember we said it's variable, and it's variable based on direction and length and all of that. So that's what we have with all of these. So this is showing the drug here in the middle bound to the receptor. So everything that has these amino acid codes and a number, right, these are all part of the receptor for this drug. These are two water molecules that are bound along with the drug and actually help transfer a hydrogen bond chain to the protein itself. So they made use of all of this, and they actually got a potent ligand at this particular receptor, which turned out to be very important. It's actually a marketed drug with regard to as an anti-cancer agent.